Hello everyone, another video today, 4.B.3. We're going to be talking about reaction diagrams. These are sometimes called Arrhenius diagrams, although Arrhenius plots are something slightly different. After Arrhenius, the guy who also did acids and bases, kind of a big chemist guy. I'm going to jump off to the side so you can copy down this graph. Very few notes in this video, but we're going to talk about what this graph means. You've seen it before. It's kind of a huge deal in chemistry, so I'm going to jump off to the side, copy it down, and I'll come on back. Alright, I know there's a little bit of a glare, but this graph right here, essentially we start with our reactants, alright, we go up over this hump, and we end in our products. Okay. Now that hump is called the transition state. It's also sometimes called intermediate state. Transition state is just during the reaction, okay, and we'll talk about what that means in a second. And then the size of this little hump right here, that's our activation energy, or our E sub A, our energy of activation. So how much energy it takes for the reaction to proceed. So our transition state, let's say we have a hypothetical, I don't know. Okay, let's say we have this compound Y, or X bonded to Y, and Z comes in here. It's going to be a single replacement reaction. So Z is going to take the place of X. Okay, so we have X and Y going over to Z. So our overall reaction, I should probably write up here, ZY plus X. So this is our overall reaction. So all that's going to happen is X and Z are going to switch places. Okay, so Z is going to come in here and bump X out. Okay, and just see what you have. So our reaction starts. So these are our reactants. So we are right here still. These are our reactants. Nothing's really happened. What's going to happen is Z is going to come on in. It's going to have sufficient energy, meaning it's going to be coming in at a sufficient speed to come up over this activation energy hump. So it's going to have enough speed that it can come up and over. All right. Now, if it didn't have enough speed, it would kind of just bounce off of Y and not do anything. Or if it came up and hit X, it would just bounce off of X and not do anything. All right. We need the proper orientation. It needs to hit Y in the proper spot, which is probably directly opposite X. And it also needs to have enough speed that it can actually latch onto Y. So what's going to happen? These are our reactants. Our transition state, which I'll abbreviate TS, don't confuse it with T.S. Eliot, it's a different guy. So our transition state, what's going to happen for a brief second, for a brief millisecond, Z is going to come on in, it's going to bond with Y, and for a brief second, Y will be bonded with both of them, right? Because the bond will form with Z, and as it's forming with Z, it'll be breaking with X. So let me show you what that looks like. So our product would then be X. So here's our product. So here, X has broken off. But for a split second, for a millisecond, they're both going to be bonded to Y because the X bond will form before the Z bond can break. So for a brief second, we'll have two bonds here before X comes off. Okay, so Z is going to come on in. It's going to form a bond, and then it's going to break. So this transition state is right up here. Notice it has the most energy, so it is the least stable. Things with a lot of energy are very unstable, right? Okay, so think of like a piece of wood or something like that, or let's say, not even better, a chip, a potato chip, okay? A potato chip has a lot of energy, and I know this because I could eat it and it will give me its energy, or I could light it on fire and it will burn. All right, it's called calorimetry. That's how we determine the calorie content of foods. All right, so those things have high energy. A chip is relatively unstable. All right, it'll burn. I can eat it. So a chip is unstable, has high energy. Water, on the other hand, very stable, very low energy. You can't do anything with water. It doesn't really react very well. You can put a pot of water on the stove and it's going to take a long time to boil because it just has so little energy. It's so stable. It's right down here at the bottom. This is low energy, is very stable. High energy, like oils, hydrocarbons, so like the gasoline in your car, has high energy. That's why we put it in our car. You put water in your car, it's not going to run because that is very low energy. It's very stable. So here, this is high energy, unstable compound. So we go from a reactant, which is a X and Y bond plus Z. Z comes in, forms this high energy transition state. And then we have the bond breaking. The last but not least, let's say we want to lower this activation energy. There's a couple of ways we could do it. Well, there's really one good way. We could add a catalyst. Okay? A catalyst is signified by this dashed line, lowers the activation energy. And it does it by targeting this step right here. Okay? It does it by targeting this step. So it changes our transition state, right? Our transition state of our original reaction is here. Our catalyzed reaction is lower. So let's say we add a catalyst. We could add a catalyst to this reaction, and let's say the catalyst's job is to break the XY bonds. Okay, so a catalyst comes in and it breaks all the XY bonds. Well, now my transition state is going to be X plus Y plus Z, right? Right here. Right, so a catalyst will come in, and let's say we've added a little catalyst, and it breaks all of these bonds. Goes through. It's like I picture it like Pac-Man, kind of, eating all these bonds here. And so what happens is we end up with these three things all together. Well, this is lower energy than this, right? This has two bonds, very unstable. It's going to start breaking. This is a little bit more stable because there's 0 bonds in it. So a catalyst, and I'll signify this by a dash line. I probably should have grabbed more than one colored marker, but I didn't. This would be a catalyzed reaction. A catalyzed reaction changes my transition state to a lower energy transition state, meaning Z now doesn't have to have as much energy, right? Because it's not busting in and trying to form this double bond weird thing here. Instead, it's just kind of floating around, and it just hooks up with Y. So this is a catalyzed reaction. It's a way to lower the activation energy required. Okay, so hopefully that made a little bit of sense. This is a very, very important concept. One last thing. Let's say I want to speed up a reaction. I would add temperature. Temperature would help get that Z particle moving quickly enough to bump into that XY particle. All right, that's really what the temperature is. It's not that they collide more often, it's that it collides with more force and really kind of latches on there. In fact, we could do the Arrhenius equation. There's an equation. It's a whole bunch of gobbledygook, but the important thing is that it's raised to the T. So like rate equals blah, 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 blah. I'm just going to that's not even real things. There's an E, and it's raised to the T value. So you know that T is in the exponent. So that way, if I double the temperature, my rate goes up like an insane amount. So in the Arrhenius equation, the important thing to know is just that T is an exponent, so increasing temperature increases the rate exponentially. Okay, so hopefully that cleared it up, and I will see you in class.